For the first time ever, I am thrilled to say we have an official sponsor for the Dirt Talk podcast, and that's Ariat. I've worn Ariat boots on every job site I've visited over the years, traveling in them across 5 continents. More importantly, I have yet to find a single project where working folks, unlike me, are not wearing Ariat boots and workwear in every condition imaginable. And there's really good reason for that, and that's because it's phenomenal stuff. And the more I've learned about Ariat and the company, the more I've loved their brand. So with this, Ariat is offering any Dirt Talk listener 10% off their next Ariat order at ariat.com/dirttalk. That's 10% off boots, jeans, and workwear at ariat.com/dirttalk or at the link in this episode's description. With that, let's get to the show. All right, everybody. Hello. Welcome back to a Monday edition of the Dirt Talk podcast. Today, we are going to feature and explain one of the coolest construction projects I have ever seen. And I've seen a lot of construction projects over the past few years. I am certainly spoiled, but this one knocked my socks off, to say the least. And so we'll get right into it because I'm so excited to break this down for you all. And we will also have an accompanying video on this at some point, but wanted to get it into an audio format here first. So without further ado, this is Denmark's largest infrastructure project and the world's longest immersed tube tunnel. To explain the need, the Femern Belt is a stretch of water about 18 kilometers, which is about 11 miles wide, separating Germany and Denmark. And I just spent extra time to convert all of these metric units into imperial units because, it's in Europe and they speak metric, but I am here to help you all better understand. So we've got a stretch of water, 18 kilometers wide, which is 11 miles, separating Germany and Denmark. And currently, the only way from Germany and the European Union to Scandinavia is the long way. So it's up and around. If you want to look at the map, Germany and Denmark are connected, but they're connected over on the left side. So to get to Copenhagen from Germany, you have to go all the way up and around. Or instead of going all the way up and around, you can take a ferry across, which takes about 45 minutes. That works for cars and trucks, but that does not work for rail and a lot of trade. However, to facilitate better trade and decrease transportation costs, the governments of Germany, Denmark, and other European countries decided to bridge the gap more directly. So the obvious solutions here are a giant bridge or a giant tunnel. A bridge, though, was more complex than it seemed. Due to tough geological and weather conditions, the resulting bridge ultimately just wasn't realistic. And then with bridges, you still have marine traffic underneath, so you have to raise the bridge quite high, which makes it more difficult to design, so on and so forth. So they said, okay, a bridge could be possible, but let's look into a tunnel. Now, traditional tunnels, like the Channel Tunnel connecting Britain to France, are dug by tunnel boring machines, or TBMs. But the issue here was that there would need to be a minimum of 4 tunnels dug underneath the water, 2 for rail and 2 for traffic, which would result in a very, very high construction cost because you would have at least 4 tunnel boring machines, if not 8 tunnel boring machines working from either side to build all of those tunnels. This is a combined rail and traffic tunnel. The Channel Tunnel, for example, is only rail. So they just have 2 tunnels there. So the engineers went back to the drawing board, and fortunately, they still had a trick up their sleeves, which is called an immersed tube tunnel. In short, the tunnel is divided into manageable segments that crews can precast on land. Each segment can then be floated out to sea and sunk. When they're all joined together at the bottom of the ocean, voila, you have yourself a tunnel. Pretty straightforward. However, the challenge was that the longest immersed tube tunnel to date was roughly 6 kilometers or 3.7 miles long. So would this method work for a tunnel over 3 times that length? That was the question. And after doing the math, the engineers decided that yes, they could do it, and this was the best solution to bridge the gap. So the project cost is about $7 billion, and the tunnel is designed for well over 100 years of operation. And when finished, it will have 3 lanes of vehicle traffic in either direction, rail in either direction, and a service tunnel. And to put that $7 billion into perspective, we are in the United States building a little over a mile of Amtrak tunnel right now in Manhattan for $15 billion. So $7 billion, a bargain for this. And they'll use tolls to repay the construction costs back over time. The tunnel will cut 150 kilometers or 93 miles of driving or rail off the current journey and will take only 10 minutes by car to cross. A substantial improvement, that is for sure. The construction officially began in 2020, and we had an incredible project tour this July. Like I said, it's easily one of the craziest projects I've ever seen, and I was I just blown away the entire time we were there. So with that background established, let's discuss how they're building it. And I have combined my boots on the ground research with a lot of the information about this project online to develop this podcast to ensure that it is as factually correct as possible. So the first step in the process is dredging. A consortium between 2 of the world's largest marine construction companies, Boskalis and Van Oord, called FBC, led all of the marine construction works. To dig the 18-kilometer, 12-meter, which is about 40-foot deep trench, the companies used up to 70 vessels to excavate over 15 million cubic meters, or about 20 million cubic yards, of earth from the bottom of the ocean. The world's largest backhoe dredges worked on the project, the Magnor and the Goliath. The companies also used trailing hopper suction dredges to suck up the earth from up to 40 meters or 131 feet deep, then discharge it along the Denmark coastline. And if you haven't looked up how trailing hopper suction dredges work, they're pretty fantastic. In short, they're giant ships with enormous vacuum cleaners that lower to the bottom of the ocean. They drag the vacuum cleaners along the bottom of the ocean, sucking up the dirt into then these giant storage hoppers within the ship. And then the ship can go to shore and either hook onto a pipeline or can shoot the material out in front of the ship to build new land. Pretty neat. And so the resulting works created over 300 hectares of new land, which FBC is working to shape and seed for recreational and environmental uses. So they have all this new environmental land, and then they'll also have some new beaches as a result, which is just going to be extraordinary. FBC also had to build an enormous work harbor to support the tunnel element construction and the 2 portals on either side of the tunnel, which will transition from land to sea. Today, their crews are placing an exact layer of rock along the entire bottom of the trench to prepare for the elements to rest perfectly along the 18-kilometer stretch. So it's quite similar, in a way, to digging a trench for some water line or some sewer. Sewer, I think, is a little bit better because the slope, the grade needs to be just about perfect. So that's all they've done. It's just on the bottom of the ocean. So they've dug an enormous trench, and now they're grading the very bottom with gravel to make sure it's all nice and flat. But when we toured the project last month, our host repeatedly said it's less of a construction project and more of a manufacturing and logistics project. The bulk of the project is manufacturing the tunnel elements, 89 in total, with the standard elements measuring 217 meters or 712 feet long and weighing over 73,000 tons. So, how the heck do they build such enormous pieces of concrete and steel? Which is a great question. They first had to build the world's largest precast tunnel facility with over 1 million square meters or 1.2 million square yards of space and 6 assembly lines costing about $1 billion. Next, they must bring in all the materials without impacting the local communities, meaning everything arrives by ship. All of the steel, stone, and concrete arrives at the work harbor, where crews unload and stockpile it to begin the official tunnel element construction process. The harbor receives up to 80,000 tons of raw material every week. Anyone who knows anything about concrete structures knows they start with steel. And a concrete structure this big requires a lot of steel. They said they're using over 50 Eiffel Towers worth of steel for this project. And I've never seen the Eiffel Tower for myself, but it looks pretty big in pictures, and that really does help put it into perspective. That's a lot of steel. They have a separate facility dedicated to transforming raw steel rebar into prefabricated panels and other reinforcing elements, which accelerates element construction within the factory. Once produced, all the steel sections make their way to the start of each assembly line, where workers assemble the entire steel skeleton, starting with the floor. They attach the walls, and finally the top, which forms a steel structure roughly mirroring the final section, roughly mirroring what the final section will look like. It's worth noting that while the elements are all similar, they're all also different depending on where each will sit within the trench. The deepest elements will rest about 40 meters beneath the surface, requiring the most reinforcing steel. Thanks to hydrostatic pressure, the more water you have on top of you, the more weight is pushing down, the more steel and concrete you need to counteract that force. Good old math. I didn't learn nothing in engineering school. They then slide the steel skeleton into reusable forms to prepare for the concrete pour. With 2 dedicated batch plants capable of 600 cubic meters or 780 cubic yards of concrete per hour, crews can pour each segment in roughly 30 hours. And it has to be a continuous pour. All of this takes place indoors because of curing. Every segment requires the same temperature and humidity regardless of the time of year. And so this giant facility is all indoors, so everything is happening under a giant building. The elements are so long that they're all divided into 9 segments, with only one segment built within the factory at one time. Once a segment is complete, crews slide it out the other end of the factory and repeat the process 9 times in total to form one completed element. So to summarize, we have one factory over here prefabricating a lot of the steel rebar elements. The steel then enters the factory, the production lines at one end, and crews will use those steel elements to build the giant cage to support one segment. There's 9 segments total in each element. They'll then push that cage to the next part of the production line, which will have the formwork. Once the formwork is complete, then the segment will be poured. As the segment is being poured, the next segment, the next steel cage for the next segment is being built up in the first step of the process. Once the concrete is set, that is then slid out the other end The next segment, steel cage, follows, is attached to the first previously poured segment, and then they pour the second segment. They repeat 9 times over, and out the other end of the building, you have one finished element. Or else they would need a 700-foot long building, which is a very long building. So, making each element 9 pieces also has an engineering benefit, as it adds a degree of flexibility. This allows each piece to fit together better once on the seafloor. And so as it sits on the seafloor and things settle out, that element has a little bit of flexibility to it, and so it can sit on the seafloor as it should without compromising the integrity of the element itself. Each element requires about 9 weeks of work, and the production lines run around the clock. Okay, now we have finished elements outside of each production line. How do we get these into the ocean? Well, crews then work to fit bulkheads on either side of the elements, making them watertight and trapping air within the large voids. Then they have sliding gates, and they can close off the dry docks where each element rests and flood them, which will then float the elements for the first time. Tugs can then pull the element out to the deep end of the dry dock, and then the water level can lower once again, allowing the tunnel element, still floating, to now be at sea level. It's similar to the principle of ships moving within a lock. So they have a dry dock, the element is on land, they close it off, and so it's this giant wall around this element. Above land, they flood it, the whole thing floats, and then they can position it in the deep end, draw the water back down. We're back at sea level. Nice. Once it's sea level floating, tugs can pull each element out into the work harbor for some final details, and then the waiting game begins. The weather must be perfect for each element's placement. When the time is right, tugs will tow the elements to either end of the tunnel and begin placing each on the seafloor. They'll flood the ballast tanks within each element with seawater to sink them. As they position them within the trench, crews have a tolerance of less than 12 millimeters, which is about half an inch, which is just completely mind-boggling. Once roughly in position, hydraulic jacks pull the elements together, initially locking them together in place. Then the water between each element is pumped out, creating a vacuum. This vacuum pulls the elements together to create a watertight seal thanks to an outer rubber gasket that is previously fit onto the elements. Workers within the previous element can then remove the bulkheads and install an inner rubber gasket to finish the connection between each element. These gaskets are also critical because they'll allow the tunnel to expand and contract as the water temperature changes. As mentioned, crews will work from both the German and Danish sides simultaneously. As more elements are placed, extending the tunnel, crews will simultaneously build the roadways and railways within the tunnel, advancing with each new element. Once in the middle, a special element will connect both sides with the ability to expand to ensure a perfect fit. And so they'll start floating these elements as they're building them out into the ocean and start placing them on the German side and the Danish side. And as they place them, they'll connect them together, remove the bulkheads, and then the crews from each side can start building the interior of the tunnel as they're still placing elements. And so it's basically 2 crews working to meet in the middle. And then once they meet in the middle, they connect both sides, they finish the interior, voila, you've got your tunnel. After the entire tunnel is completed, FBC will place layers of rock around the tunnel, and then over time, currents will completely cover the tunnel with sand, restoring the natural seabed. The first elements should arrive at their final resting place later this year, and overall tunnel construction should end in 2029. And so that is my best explanation as to how all of this is happening. It is so simple. It's like a kindergartner thought it up, but it is so complex from an engineering standpoint that I think only the Danish and the Dutch could pull something like this off. They're just incredible at engineering. But words probably, I know they don't do this project justice. And so if you want to learn more about this project, I really, really, really encourage you to go to Femern, FEMERN.com to check out the videos and information, because it's all fantastic. The animations are so helpful. There's some of the best construction project animations I've ever seen. And the entire website is extraordinary. It's so much helpful information. It has project photos. I think you can see a live feed of what's going on the job site right now. It's spectacular. So really, really encourage you to go to the project website. And they were some of the most accommodating hosts we've had on a job site like this before. Typically, some of these big job sites are very complex and very hard to visit for whatever reason. They're so much harder than they should be to visit. But these folks were remarkable, so helpful and so accommodating. And so I can't thank the entire FLC and FBC teams enough for having us. I really, really, really enjoyed it. And I encourage you to learn more about this project just for fun, because it is an amazing feat of engineering. And finally, like I said, we'll have a video out on the construction process soon. We're working on it behind the scenes. I'll let you know when it's out on social media. Thanks for listening. If you have a project you want me to highlight, dig into, if you've seen me cover a project on social media that you want more context about, send us a note, dirttalk@buildwit.com. I would love to hear from you, love to learn about what you want to learn about so that I can hopefully put it together and deliver. Thanks for listening. We'll see you next time. Stay dirty.